गुड मॉर्निंग टू एवरीबॉडी। आज हम एमएससी फिजिक्स में सेमेस्टर फर्स्ट में क्लासिकल इलेक्ट्रोडायनेमिक्स में यूनिट फर्स्ट में जो टॉपिक डिस्कस करने जा रहे हैं वो है इलेक्ट्रोस्टैटिक्स। लास्ट टर्न पे हमने इलेक्ट्रिक फील्ड निकाला था ड्यू टू द डिफरेंट टाइप्स ऑफ द चार्ज डिस्ट्रीब्यूशंस। वी हैव समराइज्ड दिस वन. First, for the discontinuous or the discrete means the charges are distributed in the non-uniform. Then we can write 1 by 4 pi epsilon naught sigma I equal to 1 to n qi r minus ri divided by r minus ri power 3, where the source charges are present at the ri and the field point is at the r. Similarly, if the charge distribution is the linear and the linear charge density is the lambda r dash, then we can write the electric field due to this linear charge distribution is E linear equal to 1 by 4 pi epsilon integration for the line integral lambda r dash dl dash r minus r dash divided by r minus r dash whole cube. Similarly, if the charge distribution in the surface form, then the E surface can be written 1 by 4 pi epsilon naught integration for the surface sigma r dash dA dash r minus r dash divided by r minus r dash cube. And for the similarly volume 1 by 4 pi epsilon naught integration rho r dash dv dash r minus r dash divided by r minus r dash power cube. If in a system all types of the charge distributions are present like the discrete, linear, surface and volume, then what is the net value? We can add in the vector form. So the E net equal to the Ed vector plus the El vector plus Es vector plus Ev vector. So all are added. Now the very important topics for this electrostatics, that is the Gauss law, Gauss प्रमेय, Gauss theorem. What is the statement? The normal component of the electric field or the net outward electric flux over any closed surface, that is called the Gaussian surface, is equal to 1 by epsilon naught times of the net charge enclosed by the surface. Means the outward net electric flux is equal to the total charge divided by the epsilon naught, that is the permittivity of the medium. So in the integration form we can write the integration for the closed surface E vector dot n cap dA q by epsilon naught, where n cap is the unit vector of the perpendicular area for the dA, q is the net charge enclosed by the surface. For the charge plus inside and outside the surface, we can obtain the Gauss law. For the first, the charge is inside the surface, given surface, let the q is present at the origin O and the point P at the surface. For the closed small surface, that is the dA, the direction of the electric field is the E and the direction of the area is the n cap, which is perpendicular to the surface given, and the angle between the n cap and E is the theta, and the distance from the O to P is R. So we can write the electric field at the point P due to this charge Q is E vector equal to 1 by 4 pi epsilon naught Q multiplied by the R vector by the R cube. And if you want to calculate the surface integral of the electric field, to calculate the electric flux, we can write closed path for the surface E vector dot n cap dA. So that is Q by 4 pi epsilon naught integration R vector n cap dA by the R cube. If you substitute the value of the E vector here and the R vector n cap, we can write R cos theta. So the inside the integration we obtain Q by 4 pi epsilon naught R dA cos theta by R cube. So what we can write dA cos theta by R square, and this is called the solid angle, the angle formed by this area dA at the center, and that is called the 3D angle subtended by the area dA at the point O. And we know very well for the net, the solid angle for the entire surface is the integration of this one, for the closed path is 4 pi. So we can write Q by 4 pi epsilon naught multiplied by the 4 pi, and we obtain Q by epsilon naught. So it is the proof for the charge present inside the surface. Now the second point, at external point, if you want to calculate the electric field, then how we can write? Let us suppose charge Q is found outside the surface then there will be the two surfaces found at the point P and Q, that is the small q, it is first is the dA2 and second one is the dA1. So here the direction of this vector area is the n cap, it is in the opposite direction of this one, the n cap, that is the dA2. So we say the net flux, one is the outward and second one is the inward, so the net flux is 0. So the angles, solid angles subtended by the area dA1 is opposite of the dA2, so we can obtain the integration of the E dot d n cap dA equal to the 0. So there is no net charge inside the closed surface, so the net outward flux will be the 0. If we summarize these two, then we can write the integration of the surface E vector n cap dA equal to the q by epsilon naught if the q lies outside S and the 0 if the q lies outside S. If more than one charge are present inside the surface, then we write the net charge equal to sigma of the q by the epsilon naught. So this is equal to the flux. If there is the continuous charge distribution, we can write q equal to the integration rho dV. So this formula is converted into the net flux, outward flux equal to E vector n cap dA equal to the rho dV by the epsilon naught. This is the integral form of it. Now, if you want to obtain the second form of the Gauss law, that is the differential form of the Gauss law, if the distribution of the charge inside the closed surface is continuous, then as earlier we can write q equal to integration of the rho dV. So the Gauss law for this one, we can write the integration over the Gaussian surface as E vector n cap dA equal to the volume integration rho dV by the epsilon. By Gauss divergence theorem, we can convert area integration into the volume integration. So for that we are using the surface integral for the A n cap dA equal to the del dot A vector dV. So using the equation second in for the first, we can write integration for the closed path E vector n cap dA equal to the integration for the volume integration del dot E dV equal to the rho dV by the epsilon naught. So finally we can rearrange del dot E minus rho by the epsilon naught integration over the dV. So del dot E equal to rho by epsilon. This is the differential form of the Gauss law. Now another equation of the electrostatic and the scalar potential. This is the line that is given in our syllabus. As we have calculated the electric field, it is the well known, it is the vector quantity. Now to represent the electric field strength in the another form, that is in the scalar quantity form, and that is the potential. So how we can obtain the potential? To obtain equation in this form, the scalar functions, we have to use del dot A equal to 0. If the curl of vector field is 0, then the vector field can be expressed in the form of the gradient of the scalar functions. So for to obtain the above equation del cross A, A should be written as the gradient of the S, where S is the scalar function. So finally the answer, because the curl of the gradient S equal to the 0. So for the electric field which is follow the above conditions, curl A equal to 0 or del cross A equal to 0. So it can be expressed in terms of the scalar functions, that is the potential. So now to prove del cross A equal to 0. As per we have calculated the value of the E for the source charge, we can write E vector equal to 1 by 4 pi epsilon naught integration summation for the I equal to 1 to n q I r minus r I divided by r minus r I power 3. If you want to curl of it, then the curl of the E equal to the 1 by 4 pi epsilon naught sigma of the qi curl of the r minus r vector divided by r minus r I power cube. If the curl of the S A, we know very well, S is the scalar and the A is vector. So we can write S equal to S dot curl A plus gradient S cross A. Where S is scalar and A is vector. So here in above equation first, r minus r vector are the vector A, and 1 divided by r minus r power cube is the scalar S. So to obtain this one, we can write 1 minus 1 divided by r minus r cube del cross r minus r dash plus gradient of the 1 divided by r minus r cube multiplied by the r minus r dash. But the curl of the r minus r dash equal to 0 because both are the del by del r, so it will be the 0. And the gradient 1 by r minus r cube equal to the, if you want to write gradient equal to I cap del by del x plus g del by k cap del by del z, and this r cube equal to, we can write x minus xi power square plus y minus yi square plus z minus zi power minus 3 by 2. And to obtain this one, we can write for the only the x component I cap minus 3 by 2 multiplied by the 2x minus xi, the whole bracket that is contains minus pi by 2. So here this is equal to the minus 3 I cap x minus I plus j y minus y I plus j cap, this one divided by this one power whole power pi by 2, and this is equal to minus 3 r minus r dash divided by r minus r 5. So curl E equal to 0 because we have write gradient of the r minus r dash equal to 0, and here this is 3 multiplied with the r minus r I divided by r minus r power 5, not 3, this is 5 multiplied by r minus r dash, this is equal to 0. So the curl of the E equal to 0. Curl of the E equal to 0, so we can write this is in form of another form, and E equal to 1 divided by 4 pi epsilon naught rho xi x minus x dash divided by x minus x dash power 3 dv, but x minus x dash divided by x minus x dash power 3 को हम लिख सकते हैं minus del of the 1 divided by x minus x dash magnitude of this one. So gradient of the 1 by r can write minus r vector by the r cube. कैसे लिखते हैं इसको? del of the 1 by r को del होता है I cap del by del x something multiplied by the 1 by r को लिख सकते हैं x minus x square y minus y I square plus z minus z square minus power by 1 by 2. डिफ्रेंशिएट करते हैं इसको तो सिग्मा I 1 by 2 minus into the 2x minus xi power जो भी आता है minus 3 by 2, and this gives minus I cap x minus si r cube, and this is minus r divided by r cube. So this is the gradient of this one. So for the above equation we can write E vector equal to 1 divided by 4 pi epsilon naught minus rho x dash del of the 1 divided by x minus x dash magnitude dv. So this is the del of something, and this del is called the potential of it. So this is another form of this one to obtain the potential form. Okay, this is all about for this one. Thank you.